Hello, and welcome back to my channel, my advanced number theory. You know who it is. It's me, your boy, the lumber snack. And last episode, we recognized that 4 can exist without 2. And our symbolic representation of 2, is to account for the fact that there is this force that appears to be conceptualized in the number 4. And so our symbol of 2 is to account for that grandiose, bigger concept. And so we remove that. How do we remove that? By introducing quaternary. And why does quaternary account for that? Because quaternary accounts for the number 7. Why does quaternary account for the number 7? Because it's 0, 1, 2, 3. 0, 1, 2, 3. That's how we account for 7, because it's a base 4. So, underneath we have 4. And so that's why there's 4 digits right there. So we've accounted for 4. We've accounted for the fact that this symbol of 3 exists. And because 4 plus 3 equals 7, we've accounted for the number 7 in our decimal series of notation. And so it then becomes, all right, where do we go next? And the next logical answer is, we know that this 3 exists as a symbol and only as a symbol, this conceptual 3, because we have the 3 right here. And in binary, it's 1, 1, which is the same as 5. So the 3 and the 5 are naturally connected by something. We don't know yet, but we do know that this 7 exists without the use of that conceptualized 3, that, pure aspect of the number 3. This 7 exists without it. And knowing that 7 is only 3 plus 4, we can assume that 7 is that 4 constant that we are accounting for. But we still have the 3 and the 5 that are tied together. Now, how are we going to split them up? Well, the easy answer is with another type of base notation. So we use the top to associate for the concept of 4. We use base 4 notation to associate the concept of 4. Well, the difference is that the concept of 4 is starkly different than the symbolistic representation of 4, to the same degree that 3 as a symbol exists outside of 3 as a concept, And so we think, how do we go about this? The easiest way is to move this 4 up here, and then we're left with a base 5 notation. And so you think, all right, cool. So we're just going to go base 5 notation to account for 5. Well, hold on there, Skippy. We can't just go with the 5 at the exact same rate and pace, because that's not going to prove anything. We have to have a reason why we need to separate this base 4 notation and this base 5 notation. What is the common mediator here? And you think, well, this base 4 notation has this symbol of 3, which exists in the 3rd space. We also have this symbol of 5, which exists in the 5th space, marked by 1 and 1, this twice. And so you think, okay, so we need to account for that. We need to account for this 1, 1 concept, this yes. Because without this, we don't have any building blocks for larger numbers, because 0 is just a concept. 0 is just a symbol. And so we think, all right, so how do we do this? How do we account for 5 and simultaneously account for 3? And the way that I've figured it out is, because quaternary and binary are accounting for this integer right here, we're using this base 5 notation, this guy right here, in order to account for this guy. this guy right here. And why does that make sense? Because if you look at the difference between, 5 and 0, you look at the difference between 5 and 0. You have a 1, you have a 4, you have a 3, and you have a 2. Now, this range, or better yet, this range right here, because we're not going to count the 0, because the 0 and the 5 are just stopping gaps. But we take this range and we take this range and think, okay, cool. So this 1 and 2 exists before the midpoint of this conceptualized 5, whereas this 3 and 4 exist after the midpoint of this conceptualized 5, And so you think as well, 4 is in this rung right here because 2 plus 2 equals 4. And so this added to itself tops and trumps this, but this guy is still halfway past the point of 5, halfway of 5. So we account for that with this base 5 notation to account for 3 by only increasing the tally when a multiple of 3 is present. Because we're counting by 3. We're increasing the tally mark for every time that we see an instance of 3, because we need to account for that 3 concept. And so once we've got that tally, we then go through and we go, okay, cool. So what's a multiple of 3 and what's not a multiple of 3? Well, 3 is a multiple of 3. 4 is not a multiple of 3, so we leave it at 1. 5 is also not a multiple of 3, so we leave it at 1. And right here, you see similarly to how with binary and quaternary, it sometimes looks like it goes in on itself. This is another representation of that. This is another example of, this 5 is now becoming that 1. The 5 is becoming that 1. That starts it off. And then we go next, and it's, okay, 6 is a multiple of 3. So now we go 2, and we find this 2 right here. So that kind of goes in. And then is 7 a multiple of 3? No, it's a 2. And then we look at 7 because we've realized now that this 1 and 3 exists for 7 without the need for the 3 itself. Without the need for 2, and with accounting for 4, these 1 and 3s find themselves in 7. Now, when you're accounting for both 3 and 5, you get 2 with 7. And thus you create 1, 2, 3. The building blocks of mathematics with that 7. And we'll get more into that later. And then you just keep going on. You go 2 for 8 because it's not a multiple of 3. And you see where we got that 2 from. And then 9 is a multiple of 3. So we're going to go 3. And then we look at it, and it's 9, 3, and then 21. And we already know 21 is 21. 21 is 3 times 7. And so we get 3 right here, this 3 right here, at 9, which is 3 squared. And then you're going to keep going. So we have a 3 right here, because remember, we're still accounting for this variable. That's what this all is about. We're accounting for this variable using this integer series, this 0, 1, 2, 3, 4. To account for 5, we're accounting for 3, because 3 is the natural point forward past the midpoint. And then we keep going until we have a multiple of 3. And then right here we see another range, because that's all we're doing is we're establishing ranges. So between 9 and 11 is a range of 3. Before we get to the range of 4, starting at 12, because 3 times 4 equals 12. And that's how it works. This is based in 4. Now you get the 4, and so you multiply, and you get the 12. Then you just keep looking for the multiples. And then right here, just like how we had 10 at 4, we get to go to 10 right here, because 15 is a triangle number. Similar to how 10 is a triangle number because 4, 15 is a triangle number because 5. And triangles have 3 sides, which is why 15 is 33, and it breaks down to 10. So let me just keep going. Because of the way this slow, measured, weighted base 5 notation is, 16 keeps its value of 110, so we keep that constant. And then we've established another range. We've established a few, so we see the 4 range at 13 because 1 plus 3 equals 4. We also see it right here because 7 times 4 is 28, so 7 times 2 is 14. That's at 32. And then we see this range right here, 15 to 17. That's important for going further with this. And then 18, we have 11 because it ticks up. And so you think about how we had 1, 1 right here for quaternary, and we had 1, 1 right here for binary. Now in this measured, weighted by 3 base 5 notation, quinary, we've got 11 at 18, which is 9 times 2. And you got 102, which is flipped right there. And you just really, as you go through, you start, you notice these number patterns that are pretty difficult to ignore. Like, for example, 21 is the reverse of 12, and both together are 3 ones in quaternary. We're just going to keep going because we're establishing ranges. That's all you do in math, is you establish ranges. And then we get 13 here at 24, which is really... I keep worrying that I've messed up, but I'm right so far. 11, 12, yeah. And you get that at 13 at 24 because 6 times 4 equals 24. And it's kind of like a weird hybrid number that uses 3, right? Because 24 is also 8 times 3. So that's why that 3 exists right there. And so we keep on going. We got another 13 range, which 13 is a Fibonacci number. Another 13 range because 26 is 13 times 2. And then we go up to 14. 14. And I'm going to make sure real quick that this is... we think about how we need this 7 in order to get all these decimal numbers. And so 27, which is 9 times 3, or 3 cubed, where we get that 1, 2, 3, we also is where we get 1 and 4. Because again, this is an explanation of the full range of our number concepts in this number 27. And the more we go into this number theory course that I've concocted, because I've discovered stuff over the past, few months that, you can't learn in college, so might as well share the information. Lumber snack guarantee. And then, we see in that 14 range, we also get 28. Because 28 is 14 times 2. And that's where you get 130. And then we just keep going with these ranges. We keep going with these ranges, and then we're at 20. We're at 20 with 30. And so this is a point where the numbers kind of start splitting off, The decimal 10 notation is going to get bigger, and the base 5 notation is going to stay at this lower rate the entire time, however, being ever present in this, So we're just going to keep on going until we get to 33, which is 21. And we see 21, or 33, and then we see 201 in quaternary, and then we see that 1 and that 2 bridge the gap with that 0 in the middle until we become 21 in this modified quinary. We keep going. We see that that 21 is present in that 34, which that 2 is absolutely necessary for that conceptualized 34, which what is 34? But 17 times 2, You got that 17 right here, multiply it by 2, and you get 21. So that's another example. And then you just keep on going for the ranges. Then 36 is a multiple, and we get 22. 6 squared, 9 times 4. You get 22 in this quinary. You get 210 right here. And you just keep going. That's all it is just you keep following the patterns until nothing makes sense anymore, or everything makes sense. We got 23 at 39, which is 13 times 3. You got 213 right there. And then at 42, you get 24. Now this is a big one. This is a big one right here. This range of 42. Why is this one a big one? Because, you know, this is full of 2's. This is 42, and we see a reflection of that 42 in this 24. And how do we get to 42? Is 7 times 6. And so a lot of mathematics is literally to account for this area right here, this conceptualized area right here, which exists simultaneously between this point, 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 and between this point. It simultaneously interacts and exists, and it's foundational for the way that we, you know, carry on with equations and how numbers get possessed, is because we're always trying to account for this phantom variable in between the numbers, right at the middle. That's why probability exists. That's why stats exist. That's why numbers exist, why we need the math to do what we need to do. It's really something in this number in order to account for it, you know. And so we're going to keep on going. We found the 24 range, which is also where we get 4 repeated. And then at 45, we're going to dip up to 30. We're going to dip up to 30 because 45 is 9 times 5. And so multiples of 15 are going to get this treatment right here. We can tell that, and we know that's something that tracks because we have this concept with this 33. So we know, so we're finding that as why the reason is. And then right here at 48, we get 31. Why is that important? Because this is where it goes up to 300. 31. 48 is 96 when you multiply it by 2. 48 is 24 times 2, as is. 48 is directly 1 behind 49 for the same fact that 49 is directly 1 behind 50. And 48 happens to be extremely composite with even numbers. You know, 8 times 6, you know, 4 times 12, 3 times 18, no, yeah, no, 3 times 16, yeah, 3 times 16 is correct. And so you see that right there. And then you just keep going, you know. We see why 31 behaves right here is because we see that 301 representative in the 49. And then we go right here, and then we hit this 50 point, and then we push forward. And rather than getting 33 with this 303, we now get 32, showing that these 3 symbols and these 3 symbols are not directly related. They are close, but they're not directly related. And we look at 51 as well, and what's 51? That's 17 times 3. So we have 17 right here, 101, times 3, and we get that 303. But it's at 32. It's in a completely different conceptualized realm as a multiple of 3, which is something interesting. Or I guess than a typical multiple of 3. Then we get 32, that 2 is reflected, and we got that 31 pushing forward. 32 again. And then right here, we get 33 at 54 because this is 9 times 6. So for the same fact that we get 33 right here at 15, we're again seeing a similar thing with an interaction between 9 times 6, providing 33 down here, 3, 1, 2. And then we continue that. And then we look at, 55, how it kind of, not only is 55 a Fibonacci number, it's 5 and 5. So for the fact that 11 exists, 1 and 1, and we already accounted that 1 and 1 exists because 5 behaves the way that it does. We've got the 11 right there and we've got the 1 right there. We then see the 55 being a representation of this 5, 5, 5, 5, 1, 1, 1, 1, 5, 5, and then you got 3, 1, 3. And then as you add its own notation to account for the number 3, or the concept of 3, you get 33 at this 55 spot. That's important, and we'll go over it more later. And then we're just going to keep going for the multiples. 56 is 7 times 8. And then 34, another Fibonacci number. So we see this Fibonacci number, 34, which is 17 times 2. And we find that at 321 in 57, which is, 7 times 19. And then we're just going to keep going. We're just going to keep going. And then we're at 60. And we're going to boost up. Because remember, any multiple of 15 boosts up. And that's what this is to account for. This whole thing is to account for this number right here. Because this number right here is the representation, the concept of this number hybridizing with this number at the same rate, at the same concept that this number is, merging with this number to get this number. To get this number directly past 5, 15 follows a similar rate, And so we just keep going. And then we hit 41 at 63. Which 41 is important because of this 5279. Now, what we're going to do real quick before I decide that this video is over, we need to figure out, okay, what is the next step? Where are we going with this? So now, through the courses of logic, from the decimal 10 notation, we've removed the 5 constant. We've removed this constant from this with binary. Then we've reintroduced this concept to binary to account for this concept and to account for this symbology. And now we are trying to account for this symbol, this concept, with this concept symbolically, with this. So now what do we need to account for? What's the next steps to account for this? What are we looking to do with this further? So I don't really know how much we have to do to anymore, because we've got binary, we've got quaternary. There's not a whole lot of representation outside that 5 times 2 equals that rounded number 10. So we need to eventually account for that in ways that are not binary. We'll get to that later. We still have roughly accounted for 3, but because of the nature of 9, we haven't been able to truly account for that, because 9 has more to it than any other number. And we can see that with the 21 and 3 right here. We can see that with the 27, 1, 2, 3, 1, 4. We can see that we need to account for a lot more with this symbol right here. So what's the next step? And the next step is a logical answer for 7. We need to fully account for 7 because 7 purely accounts for itself. We haven't accounted for 7. We have accounted for the concept of the symbolic number representation of 7 with this quaternary. But we haven't isolated that original, reason for 4. Why do these cardinal numbers exist? Because, if you don't know the modality of numbers, there's 1, 4, 7, and 10 for the cardinal numbers. Then you've got 2, 5, 8, and 11 for the fixed numbers. And then you've got, 3, 6, 9, and 12 for the mutable numbers. And so how do we account for that? How do we account for that conceptualized 4 that's necessary for every piece of mathematics, every facet to human reality, and why 7? And I want to thank you for watching. If you watched all the way, I want to thank you for potentially liking my video or commenting. I hope you comment on ways that the patterns kind of lined up where you're like, oh my goodness, that is incredible that it would behave like that. That it would behave. And so, yeah, I hope you have a great day, and I hope that you come back to my channel. Thank you for watching.